All right, guys, we're going to move into section 7.1 now. Now, this section is a really, really long one at the beginning of a whole new chapter that is a little bit unlike what we've been discussing recently. It's a whole new kind of function out here called exponential functions, and we're going to start talking about that now. Now, as you can see on the left side of my page, this is a really long section. I think I've got 19 slides here. We're not going to get through all of them in this video, but we'll just get started. Now, the first thing I wanted to talk to you about here is actually something that isn't directly related to what we're talking about in this section, but kind of explains why this is different from what we've been doing before. So if you take a look at what's going on right here, we've got a population of rabbits, okay? And it says it increases by 10 rabbits per year, and beginning with a population of 20 in the first year, which we're just calling t equals 0. So we're just going to fill in a quick table and graph what this is going to look like. So our number of rabbits in year 0, we start off with 20, but this problem tells us that the population is increasing by 10 per year. So 1 year down the line, we're going to add 10 rabbits to our population and have a grand total of 30 for a growth of 10 in that 1 year. And we're going to keep this nice and pleasant and say that no rabbits are going to die off. We're just talking about increasing. Now, if we keep going a couple years down the line right here, in the second year, we're going to add another 10 rabbits and get a population of 40 for a growth of 10 yet again. And in the third year, we add 10 more, and we now have 50 rabbits for a growth of 10. And I think I'm just going to do one more. In the fourth year, we're going to add 10 more and now have 60 rabbits for a growth of 10 again. And on the very next slide, I wanted you guys just to kind of plot out what this thing might look like, although I'm not going to take too much time on this. But in the first year, we were dealing with 20 rabbits right here. And, that was in year 0. In year equal 1, we were adding 10, so that would get us up. Let's see, if that was 20, this would be 30 right here. In the second year, we were up to 40 rabbits. In the third year, we got up to 50. In the fourth year, we got up to 60. And so our graph looked really, really simple, everybody. We have a series of points which are all collinear. And so if we connected those points, we would get a linear function. And that is why, if we go back on the previous slide, what I had written really, really small there, that was pretty much impossible to read, what we're dealing with in this particular model here is called a linear growth model, because our population increases by the same amount every year. The growth remains constant from 1 year to the next. And by the way, that growth right there is the slope of this line. We're adding 10 rabbits. That's our rise, and 1 year is our run, so it would be 10 rabbits per year, and that is the slope of this linear function. So that's what a linear growth model looks like. And as simple and as easy as it was, it's really not very realistic. Anything we're talking about in the natural world that reproduces, whether it's an animal, a plant, a bacteria, anything like that, tends to not just add the same amount, the same number of population every year, but it tends to be based more on a percentage. A larger population is going to typically have more growth in 1 year than a smaller population. So let's go to slide number 3 here, everybody, and take a look at something similar, but it's working a little bit different. So what this problem says here is that a population of rabbits, now instead of increasing by the same number per year, it's increasing by 25% per year, beginning with a population of 20 in year t equals 0. So we're going to do kind of the same thing here. We're going to fill in this table, I think, up until about year 4. So if I go to year number 1, what I would do in my calculator, everybody, and I'd like you to do this with me here as you're following along, is we're going to take our initial population, which is 20, and we're going to multiply that now by, if we're looking for a 25% growth, we're going to multiply that by 1.25. Now, a lot of people say they just want to multiply by 0.25, but since 0.25 is less than 1, that would actually decrease the number of rabbits we would have in our population. By including the 1 in front of that, that means, okay, I want to keep all the 20 original rabbits that I had, and then I want to add another 25% to that. So I'm doing this on my side right here, but if I now take 20 and multiply that by 1.25, that gets me a nice number of 25 rabbits here for a growth of 5 in my population because I went from 20 to 25. Now the plot thickens a little bit. As we go to point number 2, we're going to take 25 now and multiply that by 1.25. And when we do that, we start to end up with some decimal numbers, and yeah, you can't really have a decimal rabbit, but I'm going to go ahead and include that anyway, because if we're talking about money or something like that, that might be more accurate. I got 31.25 for my number of rabbits the next year, which means that my growth was 6.25. The important thing here now, guys, is that the growth from year 0 to year 1 was 5. The growth from year 1 to year 2 grew more than it had in the previous year at 6.25. Let's move on to year 3. So if I take 31.25 and multiply that by 1.25, I now get 39.0625. That's not very pleasant. And that's going to get me a growth right here of, let's see, I better subtract 31.25 from that. I got a growth of 7.8125. So again, the growth amount in this column right here doesn't remain constant, but it actually gets bigger every year. Okay, let's go back to that 39.0625 that I had, and if I multiply that, let's see, I think I broke my calculator here. All right, so if I go to 39.0625 and multiply that by 1.25, now that gets me, let's see, 48, and I'm going to start rounding here because the number of decimals gets crazy. So I'm going to say just 48.83, and then roughly, let's see, from one year to the next, that gives me a growth of about 9.77, roughly. Okay, so let's see what that one would look like in a graph if we go to our next slide. So year 0, we still had 20 rabbits, so that puts us at this same point right over here where we started the previous graph. But now in year 1, we're only at 25. So this one is actually growing at the beginning slower than the initial graph we had a few slides ago, which had that first point located up here at the point 130. So we're growing more slowly at the beginning, but let's see what happens as time picks up right here. In year 2, we're at 31.25. So 10, 20, 30, 31.25 would roughly be right about there. And as we go on to year 3, we were looking for a population just under 40, which would be probably right about there. Let's see what would happen in year 4, where our population now was, let's see, just under 50, 48.83. So 10, 20, 30, 40, 50 would be right about here. And let me go ahead and find the 5th year right here, just because I want to show you guys what that one would look like. So if I took that 48.83 and multiplied that by 1.25, now in my 5th year, I'd be at about 61 rabbits. So what would that look like on the graph? The 5th year, 61 would be right over here. And what I was hoping you guys would see, and unfortunately I don't think my graph does a great job here, is that this graph is not exactly linear like the first graph is. This one is starting to curve ever so slightly upward. And once a growth graph like this starts to curve upward, it tends to keep curving upward. And eventually, I wish I'd drawn a better picture right here, tends to take a shape that does something like this, that tends to increase at what we call an increasing rate. And that, everybody, is what an exponential growth model tends to look like. It doesn't grow by the same exact amount every year, but it grows by a set percentage. And that's really the key, the hallmark here, to what we call an exponential growth function. So this is where our notes for 7.1 really begin. An exponential function is one that's written in this format right here, which we have not seen all year up until this point. An exponential function is y, or f of x, is equal to a times b taken to the x power. What makes a function exponential is that the variable is right up here in your exponent. Now, we've done functions this year with exponents in them, but they've been something that looks like this. Now that's a quadratic function. The difference here is that in a polynomial function like this, the variable is the base of your exponent, and the exponent itself, the power, is a constant like 2 or 3 or 4. Now in an exponential function, the variable is the exponent, and it's acting on a constant for your base. So what makes a function exponential is that the variable is in the exponent, and that's different from anything we've seen so far this year. Now again, I always want to tell you guys what everything means in a formula that we learn. Y, right here, is what we call your final value. Sometimes it might be helpful to think about that as the current value too, if it's something where the growth is ongoing. So final value or current value is found by Y. That's the left-hand side of the equation. The A number, which is the constant right over here that's being multiplied by b to the x, A is what we call your initial value, and that's also the y-intercept of your graph. So in that rabbit problem that we were just working on a second ago, the initial value we started with right over here was 20 rabbits. So that's what we would have put in for A in that problem we just did. And then B, which is the second number here that A is being multiplied by, but most importantly, B is the base of the exponent here. B is what we call our growth or decay factor. Now everybody understands the word growth as something gets bigger over time, like for example our population of rabbits. But the word decay is something I just want to talk about quickly, and that just means the opposite of growth. Decay is when something is dying over time or losing population or losing value. So growth is basically going to be a positive factor. Decay is when that's going to be a negative factor. Okay, so that's kind of our explanation here of what an exponential function looks like. And I wanted to talk quickly about what can impact a function here and make it be either a model of growth or decay. And so I made a little table right here, and you'll notice we've got two different things going on. In this top row right here, we're talking about the value of b either being greater than 1 or smaller than 1. Now remember everybody, b right here is the base of the exponent. And if b was 1 itself, 1 raised to any power is always just going to be 1. So b will never actually equal 1 because that wouldn't be growth or decay. That would be something staying exactly the same over time, and that's not a very interesting problem. So the value of b is going to impact whether we're dealing with growth or decay. The other thing, and that's going on in this first column over here on the left, is the sign of your exponent here, which is x. So in the most normal case, like for example that rabbit problem that we just talked about, y is the final population. We said that a was the initial condition, and we were starting in that problem, I believe, with 10 rabbits? I can't remember now. No, we had 20 rabbits at the beginning of this group. So 20 would be your initial condition, and we were multiplying that by b, which is your growth factor. Now our number of rabbits was increasing by 25% per year, so we were multiplying that by 1.25 raised to the x power. So what's going on in this example right here? Our b value right there, 1.25, is greater than 1. So we're talking about this first column in the table. And then what happened is that x was the number of years that went by in this experiment. That was always positive. So in this case right here, guys, that is what we call an exponential growth model, when b is greater than 1 and x is greater than 0. Now, if we flip things around a little bit, if this b value here had been less than 1, like for example, if it was 0.75, that would mean that we're actually losing population each year, and that would be a decay model. All right. In this third box, the one in the bottom left right here, if that x value was actually a negative number, that also would be a decay model here. But the weird thing is, this fourth case right over here in the bottom right-hand corner, if you ended up with what looked like a decay model, but you were taking it to a negative power, that is actually a growth model. Kind of a strange one there. It doesn't happen very often, but that could pop up. So this little chart might help you guys as you're going through your notes and some homework problems here to see if we're dealing with growth or decay. All right, so let's start talking for a second here, guys, about what exponential functions look like. So we're going to start off with one that's far easier than that rabbit problem we were just dealing with, y is equal to 2 to the x. Now, this is the very first time we've ever dealt with a growth or decay graph before, other than that little rabbit problem. So I want to remind you guys that every time this year we have learned something new and we've tried to graph it, the one method that always works for coming up with a graph is simply an XY table. So let's plug in a few x values and see what happens. Always a great idea to start with 0 for your x value. So when we take 2 to the 0 power, go ahead and grab your calculator if you're not sure about this, but any number raised to the 0 power is equal to 1. So that gives us a starting point right there at 0, 1. And there's no reason to make this more complicated than we need to. Let's just start going down the list with the next biggest integer for x, which is 1. 2 to the first power, well, any number raised to the first power is that number itself. So we get the ordered pair 1, 2. And right now, I don't know if we have much of a sense of what that graph looks like. 2 points really isn't enough, so I think we better keep going. If we put a 2 in there, we're now taking 2 to the second power, and 2 squared is 4. And we're going to see something interesting as soon as we plot that point right there. Now all of a sudden we can tell that this is a non-linear function. The slope from our first point to our second point was 1, but the slope from our second point to our third point here is 2. And if the slope isn't the same, your function is nonlinear. And I think I've got room for maybe one more right here. If I put in a 3, 2 to the third power is equal to 8, which is as high as this graph is going to go. If I went a little further, it would be correct. I could put in a 4, and 2 to the fourth would be 16, but now I'm just guessing as to where that point is. And it's probably up somewhere like that. So what I think you can see as we look at these 4 dots and maybe even that 5th dot where I guessed is that this function is definitely nonlinear, but it increases at an increasing rate. It gets steeper and steeper and steeper the farther to the right that we go. But one of the things we don't often think about until somebody says, hey, think about this, is what would happen to a graph like this if we started moving in the opposite direction. So I'm going to keep going with my chart right here. I'm going to kind of put a line. What if I had moved to the left? And what if I had let x equal -1? Now this is something you guys are going to be able to use your calculator with. But when we go to take 2, let me write this here, to the negative first power, what that really means, everybody, is 1 over 2 to the positive first power. So that is just going to be a 1/2. We haven't done much with negative exponents yet in here this year. That's the way that works. So -1, 1/2 is going to give me a point that's right about there. Oh, and I don't know what I just did, but that was bad. Okay, let's go with that. If I put in a -2, we're taking 2 to the negative second power. So that's a 1 over 2 squared. The exponent becomes positive when we move it down to the bottom, and we end up with 1/4 for that y value. So -2 and 1/4 is right about there. If I put in a -3, that's going to give us 1 over 2 cubed, so that's going to be 1/8. And what you're going to start to see here, guys, is the farther left we move, these y values are going to get lower and lower and lower and get closer to 0, but never actually reach that 0 value. So we end up with a curve here that looks something like this. And that's new to you guys. That is the basic parent graph. In fact, let's make ourselves a little note right here, because that is always a good thing to know, that this right here is what we call the parent graph for an exponential growth function. Okay, so we're going to need to know that one. That's our parent graph for this particular function, y equals 2 to the x. Every other function that we're going to graph is going to be based off of this one. 4 questions I wanted to talk about at the bottom. One of them here it should be on our mind recently right here, the domain of this function, because we just got done talking about that at the end of chapter 6. And the domain is all of the x values that you can put into this function and get a real result. Well, if we look at how far this graph goes to the left, the answer to that is forever. And if we think about how far it pushes off to the right, it's going to do that same thing as well. It's going to go on forever in both directions. So once again here, guys, our domain would just be this symbol right here, which means all real numbers. Okay, you guys just have to use that symbol right there, and that's it. Now, range, we haven't really talked much about this year, but let's go ahead and start discussing it now. If domain is the set of all x values you can put into a function, the range is the set of all y values that you can get out of a function. And as we look at the graph, the fact that this thing goes up without end over here on that right means that this graph goes up forever, and there's no limit to how high the y value here will get. But as we read this thing going downwards now, there is a limit to how low this function is going to get. The x-axis, everybody, is kind of a border to this function, and it's never going to drop below that. You can take positive 2 to any power and get any positive result that you want, but you will never get 0 and you will never get a negative number. And so for that reason, everybody, let's see if I can slide this right here, maybe. There we go. Our range right here is going to be all y values greater than 0. But that excludes 0 itself, and it excludes negative numbers. So that's important. The asymptote, that's a word we haven't talked about a whole lot here this year. That asymptote is going to be kind of a dashed horizontal line right here that your function is going to approach but never quite touch. And that is this line right here that the graph gets closer and closer to, but it never touches and it never crosses. So your asymptote right here, everybody, is going to be the x-axis, which is the line y equals 0. And the y-intercept, that's the spot right here where this graph crosses the y-axis, and that's right here at positive 1. So everybody, that's our parent graph right here of an exponential function, y equals 2 to the x. And that's about everything that we might need to know about that. The next few graphs we're going to do are going to be pretty quick because they're all going to be variations on that same theme here. So let's take a look at this one. Y equals negative 2 raised to the x power. Okay, or actually, I tell you what, I read that wrong. Really should have said that as y equals the opposite of 2 to the x. So if we think about what our table of values is going to look like here, let's see what's happening now. If we put in a 0, it's important to get the order of operations right. We're going to take 2 to the 0 power, which equals 1, but then consider the opposite of that 1. So we're going to get 0, negative 1 for our first point. Putting in a 1, 2 to the first is 1, but the opposite of that, 2 to the first is 2, but the opposite of that is negative 2. So 1, negative 2 gets us that point there. Let's put in a 2. 2 squared is 4, and the opposite of that is negative 4, so 2 to the right and 4 units down. And I think we should already have a sense of what this thing looks like based on what we saw a moment ago, but just for fun, let's try 3. 2 cubed is 8. The opposite of that gives us negative 8. All right, guys. And with those 4 dots, I'm hoping we can realize that's probably good enough. This is basically the same graph we saw in the last problem, except it's being flipped down over the x-axis. So this one's actually a decay problem. It's going downward from there. Let's answer these 4 questions here. Domain, what x values can you put in? How far does this graph go from left to right? Again, there's no limit to this thing horizontally, so your domain is still going to be all real numbers. Your range, the set of all y values? Well, now as we take a look, we're realizing this time that we're only coming up with negative y values, but we'll never get a positive and we'll never get a 0. So here your range is y is less than 0. The horizontal asymptote here, yet again, let me a different color right here. We'll go green on that one. That again is going to be the x-axis. That's the line that your graph is approaching but never quite touching. So once again, that's the x-axis or the line y equals 0 right there. And the y-intercept, the spot here where this thing crosses the y-axis, is at negative 1. Okay, so this actually is something I was hoping you guys would know at the beginning. If our parent graph looks like it did on the previous graph right here, putting a negative in front of any function is just going to flip it over the x-axis down this way. So instead of opening up to the right, this one kind of goes down to the right. Okay. All right, so that's y equals the opposite of 2 to the x. Now, how about this one here? Again, similar, but not quite the same. Y equals 2 to the negative x power. And if we think about what we put, see if I can scroll that down, in our table a little while ago, which was right here, when the exponent, which is x here, becomes negative, we are usually looking right here at a decay function. Let's keep that in mind. So with that in mind, let's make ourselves a table. I'm going to switch back to purple here. And here we go. So x and y, and we'll try to come up with 3 or 4 ordered pairs and see what happens. Plugging in a 0, that looks like a heart. Plugging in a 0, we've got 2 to the negative 0 power. Well, there is no negative 0, that's just 2 to the 0, and we get this starting point again at 0, 1. Plugging in a 1, this is now going to become 2 to the negative first power. And as we said a while ago, 2 to the negative first means 1 over 2 to the positive first power, which is just going to be 1/2. So putting in a 1, we're going to end up with 1/2 now for our y value. So it kind of looks like this thing is lowering its value from left to right. If we put in a 2, 2 to the negative second power, that is 1 over 2 squared, that's going to be 1/4. So now we're even closer now to the x-axis. And just for fun, what would happen if we put in a negative number like negative 3? That now would become 2 to a power that is the opposite of negative 3. Well, the opposite of negative 3 is positive 3, and 2 to the third power is 8. So I get the point negative 3, 8, which is way up here. And hopefully that's enough to show you guys that this graph is going to fall from left to right very quickly at first, and then it kind of levels off and looks something like that. Your domain, yet again, there's no limit to how wide this graph goes from left to right. So again, your domain is all real numbers. Let's knock out the next 3 questions real quick. The range, all the y values that you're going to hit, everything is above the y-axis. So the x-axis, excuse me. So your range here is going to be y is greater than 0, not equal to 0, not less than 0. Your asymptote, yet again, is going to be this horizontal line right here at the x-axis, which is again the line y equals 0, and the y-intercept, this one crosses the y-axis right there at 1. Okay, so there's our first pure exponential decay model. And then the fourth variation I wanted to give you right here is I just wanted to show you what different things can happen when you start to put a couple of different numbers in place right here. So here we've got y equals 2 times 3 to the x power. So if you go back to the way we wrote this at the beginning here, the 2 is your a value and the 3 is your b value. You might need to go back and look at what that does and what that impacts for us. But if we've forgotten all that, you can always just make yourself a table. And putting in 0 is a great way to start. So what would we do here plugging in 0? We would take 3 to the 0 power, which would equal 1, and then multiply the 1 by the 2 to get 2 for our first y value there at 0, 2. Plugging in a 1, okay, that was weird. All right, let's take 3 to the first power, which is 3, and then multiply that by 2, we're going to get the ordered pair 1, 6. And I fear that I know what's going to happen here when I put in a 2, and we're not going to like the result. All right, let's take a look at what's going on, guys. 3 to the second power is 9. 9 times 2 is 18. And that point 218 is going to be way off my graph, and it's higher up than that, but okay, that's what that looks like. Just for fun, if I had put in, let's say, a negative 1, 3 to the negative first power is 1 over 3 to the first. That's 1/3 times 2 is going to get us a fraction of 2/3. So negative 1 and 2/3 might be right about there. Ooh, and if I put in a negative 2, 3 to the negative second power, that's 1 over 3 squared. That's 1/9 times 2 is going to be 2/9. That's even lower, and that's going to look something like that. So those 4 or 5 dots hopefully are going to show you what this thing is going to look like. Again, guys, our curve increases very slowly at first, and then it really takes off on us right there. So let's knock out these same 4 questions again. Your domain, once more, I think you guys are seeing a pattern here, at least I hope. Your domain is all real numbers. There's no limit to how wide this graph goes from left to right. Your range, if we look at it, guys, we're only looking at positive y values, never zero, never negative, so y has to be greater than zero. Your asymptote, yet again, is the x-axis here. That will change a little bit when we put a plus k at the end of all that later on, but for now, that's still y equals 0. And the y-intercept, that changed a little bit on this graph here, guys. This thing crossed the y-axis right, didn't want to do that. Crossed the y-axis right here at this value of 2. And remember, we talked a while ago that your a value is going to be your y-intercept, and that is what we had right here when we recognized that a was 2. That's where it crosses the x-axis. And the last thing I really wanted to do with you guys today is just talk quickly about what the impact is of those particular base values. So I wanted to graph 3 of these on the same plane right here. If we let y be 2 to the x, 3 to the x, and 4 to the x, what's that going to impact here? So let me switch some colors around so things actually match. And in blue here, let's talk about 2 to the x, which actually we just talked about already. The important thing here, guys, let me slide this around a little bit, is that with 2 to the x, when x is 0, y equals 2 to the 0 power, and we end up with 1. When x is 1, 2 to the first power is 2. When x is 2, 2 squared is 4. We end up with a graph that looks something like this. So without being too specific, this is the graph of y equals 2 to the x. Now, how does that change when I switch to green here, and we now try to come up with the graph of y equals 3 to the x? 2 interesting things I want you to know. First of all, when you put in 0 for this green graph here, 3 to the x, 3 to the 0 power is also equal to 1. You really end up with the same starting point. But as soon as you move right, you'll realize something different happens. 3 to the first power is 3. This jumps up higher than the blue curve we had just a second ago. And even more to the right, 3 to the second power is 9, which is going to be up here somewhere. So this green graph increases more quickly than the blue graph did. The weird thing is, though, guys, when we move to the left, the green graph is actually going to be slightly lower than the blue graph. Oh boy, slightly lower than the blue graph was. Okay, and it still has that same horizontal asymptote, but it's actually lower on the left-hand side. Most of us focus on the fact that it's higher on the right. And if you can figure that out, you might know already what's going to happen when we do y equals 4 to the x in red. Putting in a 0, 4 to the 0 is still 1, so we get the same starting point, the same y-intercept for all 3 graphs. But if I let x equal 1, 4 to the first power is 4, and if I let x equal 2, I don't have room to show you that. 4 to the second power is 16. So this red graph increases even faster than the green graph. But on the left-hand side, when x is negative 1, 4 to the negative first power would be 1/4, which would be even lower than the green graph. So it's really difficult for me to show you guys this accurately. But that red graph, I hit it again, and I lost it completely. So that red graph is even lower than the green graph on the left and even higher than the green graph on the right. And the key to this mess here, guys, is that all of them pass through this same point right here at 0, 1. That's the y-intercept for all of those. All right, guys, that's kind of a quick crash course right here in exponential growth and decay functions. When we pick this thing up next, we'll start talking about using these here to actually solve some problems here. So we've got a lot of word problems coming on a little bit later, but that's probably a good spot to stop for today. Hopefully you guys can get a jump on that 7-1 homework. Good luck, everybody.